Our video tutorial is about law of conservation of energy and Newton's law of motion. This equation is a statement of the conservation of energy, which states that the sum of kinetic and potential energy of a body as it moves from one point to another, the sum is always constant. And this equations, the summation of all forces along the x-axis and summation of all forces along the y-axis is equal to mass times acceleration. For example, a block slides down a curved frictionless track and then up an inclined plane. The coefficient of kinetic friction between the block and the inclined plane is U sub k. Use energy methods to show that the maximum height reached by the block is y maximum is equal to h over 1 plus U sub k times cotangent theta. So this is the block. It moves from point A along this frictionless curved path to point 1 and up to point 2. So from energy conservation principle, the sum of the kinetic energy and potential energy at point E is the same sum of kinetic and potential energy at point 1. At point A, the kinetic energy is equal to 0 since the body is at rest. Its potential energy at point E is equal to weight times the height of the block. At point 1, its kinetic energy is equal to 1/2 mv sub 1 square, and its potential energy is equal to 0 since the height is 0. Simplifying the equation, solving for b sub 1, our b sub 1 is equal to square root of 2gh. From point 1 to point 2, as the block moves up the inclined plane, there is other work done by the force of friction on the block, and it loses its energy as it moves from point 1 to point 2 due to the force of friction. At point 2, the free body diagram, we have here the normal force, the weight directly downward, the component of the weight perpendicular to the plane, and the component of the weight parallel to the plane. The other work done is negative because the block loses its energy as it moves up to point 2. So this is negative. Work is equal to force times distance. The force is the kinetic force of kinetic friction, and it is equal to U k times the normal force. Its kinetic energy at point 1 is equal to 1/2 mv square. Its potential energy at point 1 is 0 since the height is 0. Its kinetic energy at point 2 is 0 since the body is at rest. Its potential energy at point 2 is equal to its weight times the height y maximum. Simplifying the equation, substitute the value of b sub 1. B sub 1 square is equal to 2gh. The normal force is equal to W cosine theta, but W or the weight is equal to mg, so mg cosine theta. Cancelling out common factor, mg, and in this term cancel out 2. Simplify the equation. Then from this triangle, the sine of angle theta is equal to the opposite over the hypotenuse. So sine theta is equal to y max over s. Solving for s in this equation and substitute the value of s in this equation. So simplify. We know that cosine theta over sine theta is equal to cotangent theta. Transfer this term to the right, negative becomes positive, and y maximum is common in each of the term. Factor out y max. Then solving for the maximum value of y from this equation. So the value of the maximum value of y is equal to h over 1 plus u sub k times cotangent theta, which is equal to the given equation. Problem number 2. A block of mass m is released from rest from point E. The track is frictionless except for the portion between B and C, which has length d. The block travels down the track, hits a spring of force constant K, and compresses the spring x distance from its equilibrium position before coming to rest momentarily. Determine the coefficient of kinetic friction between the block and the rough surface between B and C. So this is the block. It slides down from point A to point B, which is frictionless, and from B to C, the surface has friction. From point C to point D, it compresses the spring a distance of x from its equilibrium position. Then it stops momentarily at point D. So our equation for the law of conservation of energy, from A to B, we have sum of kinetic and potential energy at point A is the same as the sum of kinetic and potential energy at point B. At point A, its kinetic energy is 0 since it is at rest. At point B, its potential energy is 0 since the height is 0. At point A, its potential energy is its weight times the height, y. And at point B, its kinetic energy is 1/2 mv squared. Cancel out m and solve for b squared. This is our equation 1. From point B to C, our equation, kinetic and potential energy at point B plus the negative work done due to overcome the kinetic friction. So this is negative because the energy of the body decreases due to the frictional force exerted by the surface on the block. And at point C, it has kinetic and potential energy. So the force of kinetic friction, F sub K, is equal to coefficient of kinetic friction times the normal force. At point B, its potential energy is 0 because the height is 0. At point C, its potential energy is also 0 due to 0 height. At point B, its kinetic energy is 1/2 mv squared, and this is F sub K is U sub K times normal force, and its kinetic energy at point C is 1/2 mv squared. Its normal force is equal to the weight, mg. Then simplify the equation, cancel out m. Simplify further, multiplying the whole equation by 2. Then this is our expression for B sub C, the speed of the block at point C, as equation 2. From point C to point D, our equation at point C includes the kinetic and potential energy. At point D, the energy is potential plus rather kinetic energy, potential energy, and the elastic potential energy. At point C, its potential energy is 0 since the height is 0. At point D, its kinetic energy is 0 since it stops momentarily, and its potential energy is 0. So it has only elastic potential energy at point D. At point C, its kinetic energy is 1/2 mv squared, the speed at point C, and its elastic potential energy at point T is 1 half kx square. Multiply the whole equation by 2. So this is our expression as equation as number 3. Substitute equation 2 in 3. So this is equation 2. This b sub c square. Substitute in equation 3. Then distribute m in each of the term. Then transfer this term to the left and this negative term to the right. Then solve for u sub k in this equation. So this is our expression for the coefficient of kinetic friction, which is equal to this left side divided by the coefficient of u sub k 2 mgd. So this is the expression for the coefficient of kinetic friction. Problem number 3. Consider a particle of mass m whose motion starts from rest in a constant gravitational field. If a resisting force proportional to the square of the velocity, that is kmb square, is encountered, show that the distance is through which the particle falls is accelerating from b sub o to b sub 1 is given by s equals 1 half or 1 over 2k times ln of quantity g minus k b sub o square all over g minus k b sub 1 square. So this is the particle. It moves from a certain height down to this point, or it starts from rest until it acquires or attains b sub 1. So the free body diagram for the particle, we have here the upward force, which is the resisting force, and the downward, which is the weight of the particle. So from Newton's second law of motion, the summation of all forces along the y-axis, so we have negative w, negative because it is directed downward, plus the resisting force upward is equal to me sub y. The acceleration due to along the y-axis, the acceleration along the y-axis is negative because the body moves downward. So multiplying the whole equation by negative 1, this becomes positive, and positive becomes negative, and negative becomes positive. W, or the weight, is equal to mg. From this equation, cancel out common factor m. So we have a simplified form of this equation. And rearrange this equation, E sub y, or acceleration along the y-axis, is equal to g minus kb square. Acceleration is the rate of change of the velocity. So db over dt. From the chain rule, dB over dt is equal to dB over dx times dx over dt. Cancelling out dx, we got the original fraction. But dx over dt is the velocity, or the velocity is the rate of change of the distance. So simplifying this expression on the left side and rearrange, we have here v times dv dx is equal to g minus kb square. Rearranging the term, we interchange this quantity with dx. So dx is found at the right side of the equation, and this quantity becomes the denominator of dv. So we have here, we arrange the variable. This is separable equation, separable variable equation of differential equation. Then we integrate both sides of the equation. take the integral of both sides of the equation as the value of b starts from b sub o to b sub 1. We let u equal to g minus kb square, so that the derivative of u du is equal to derivative of constant g is 0. Derivative of kb square is 2kb times db. So from this equation, du equals negative 2kb db. We solve for b db because in our integral we have here b db. So it is equal to du over negative 2k. So we replace this one. So our b db, our fraction becomes du over u. We replace b db by du over negative 2k. So du is at the numerator and the negative 2k is before the integral symbol, 1 over negative 2k. And g minus kb square is equal to u. So our denominator here is u. So we know that the integral of du over u is equal to ln of u. And integral of the x is x. Then we substitute u. We substitute back the value of u. So u is equal to g minus kb square. Then we evaluate the integral, this definite integral, from b sub o to b sub 1. And our x, this distance is x, which is s in our problem. So we evaluate this integral, substitute b with b sub 1 minus ln of quantity g minus kb sub o equals s. Then distribute the negative sign in each of the term inside the quantity. So negative times negative becomes positive of this quantity involving b sub o. And negative times positive is negative for the ln of this quantity involving b sub 1. Then we express the logarithmic form into its original form. Subtraction is the result of dividing or division. So this is ln of quantity g minus kb sub o square over g minus kb sub 1 square. Then we eliminate the grouping symbol and we interchange the left and right side of the equation. So this is the value of s, the distance traveled by the particle as it moves down against the resisting force. So it is equal to s as it moves from b sub o to b sub 1 is equal to 1 over 2k times ln of this quantity g minus kb sub o square all over g minus kb sub 1 is square, which is equal to this given equation. Problem number 4. An object of mass m is suspended from a post on top of a cart by a string of length L. The cart comes to rest after colliding and sticking to a bumper, and the suspended object swings through an angle theta. So this is an object of mass m hung by a string of length L. The cart is initially moving. A. Show that the speed b sub o initial speed is equal to square root of 2gl times quantity 1 minus cosine of angle theta. So at this point, the object swings at angle theta. We will reproduce this figure showing the angle and the length of the string. So the object is initially at this point, it swings up at this point. So we need to determine this respective distances or height. Out of this triangle, we label this side adjacent to angle theta as adjacent side. So from this right triangle, the cosine of angle theta is equal to adjacent side of the angle divided by the hypotenuse. So solving for the adjacent side, cross multiply, so adjacent side is equal to L times cosine theta. So this height is equal to L times cosine theta. And this height also, since the whole length is L minus this length, which is L cosine theta, so this height is L minus L cosine theta. So we label the points as O and point 1. From our energy conservation principle, the sum of the kinetic and potential energy at point O and point 1 are equal. So at point O, its potential energy is 0 since the height is 0. This is our reference level. At point 1, the kinetic energy is 0 since the particle or the mass stops momentarily. At point O, its kinetic energy is 1/2 mv squared. At point 1, its potential energy is equal to the weight times the height, this height, which is equal to L minus L cosine theta. Simplify, cancel out m, and solving for or substituting h with this value, then simplifying, solving for b sub o. L is common factor in each of the term inside, so we remove L outside and extracting the square root on both sides of the equation. So the initial speed is equal to square root of 2gl times quantity 1 minus cosine theta, which is the same in the given equation.